In this last video for this unit, I want to go through 5 examples of actually solving with Laplace transforms. Now that we've done all this setup work, I want to show you how it actually works. So let's start with a pretty simple example to get us going. Here is a differential equation, y double prime plus y equals 0. We already know what kind of solutions this should have, but let me show you how the Laplace transform gets there. We need initial conditions. Initial conditions are actually involved in the Laplace transform. They show up in the transform of the derivatives, so they need to be specified here. So I'm going to start with an offset of 1 but no initial velocity. So this is like a pendulum or a spring that's pulled out and held at some distance from equilibrium and then let go to start the system. So I apply the Laplace transform to the whole system, applying the Laplace transform on the left and on the right. On the right just gives me 0. On the left it's linear, so I have the Laplace transform of the second derivative and of the original. The original just gives me the new function capital Y, and the second derivative, this is the magic of the Laplace transform, gives me this expression with s squared times the function y plus or minus rather these other terms that come from the initial conditions. I fill those in with the initial conditions and I get this. This is now an algebraic equation. This is the whole point. A differential equation has become an algebraic equation. I take the minus s over to the right to become positive s. I factor the s squared plus 1 out of the y. I divide by the s squared plus 1, and I get this expression. And in order to get back to the lowercase y, then I need to invert the Laplace transform. I look at my tables, look to see if I get s over s squared plus 1 anywhere. I in fact do. That is the transform of the cosine. So the inverse of s over s squared plus 1 is the cosine, and I'm done. This is how, in a nutshell, a Laplace transform solves a differential equation, changes it into a linear, solves that linear, and tries to reverse the transform. All right, let's add a bit of complexity now. Now I have a differential equation with a first derivative term as well, still a harmonic motion with positive coefficients. I also have a forcing term. This forcing term is exponential decay, and I have these initial conditions. I apply the Laplace transform to all the pieces. On the right, e to the negative 2t, I look up on the tables, that transforms to 1 over s plus 2. Y just transforms to capital Y, so 4y goes to 4 uppercase y, and then the two derivatives transform as these two expressions involving the initial conditions. Well, then I have the initial conditions, I put those initial conditions in, I get this expression. Everything here is a capital Y except for the 2, so the 2 I bring over to the other side, and I factor the capital Y out. On the right, then I go to common denominator. Then in that common denominator, I can divide by the expression in front of the y on the left, giving me an isolated expression for capital Y. These denominators are the same, so I can write that as x plus 2 cubed. All right, now I've isolated capital Y. I can't undo the transform directly in this form. What I often have to do here is partial fractions. So I do partial fractions to split this up. I'll do partial fractions by computer, of course, at this point. And then I have these two expressions. I want to go backwards to lowercase y, but these are still a bit tricky. I'm not going to find anything exactly on my tables that measures this. However, I do have something on my tables that tells me what happens to a derivative in the s domain. So sometimes to undo the transform, we're going to have to say, oh, is this the derivative of something I understand? And s plus 2 squared, s plus 2 cubed in the denominators, these are in fact first and second derivatives up to some coefficients of 1 over s plus 2. So I can set that up, and I can understand the Laplace transform here as a first and a second derivative of these two things. 1 over s plus 2 transforms to e to the negative 2t. And the derivative and the second derivative give me multiplication by t and t squared in the t domain. So these two derivatives become this using the derivative and shift setup in the t domain. As a result, this is my solution for the original differential equation via the Laplace transform. A little bit more work here on the s domain to try and manipulate it, partial fractions, derivatives, to put it into the form where I can actually recognize what's going on. Here's another example with a polynomial forcing term. Here are the initial conditions. Again, I take the Laplace transform of both sides. The y double prime becomes these three terms using the initial conditions. Lowercase y becomes uppercase y, and I apply the Laplace transform to the quadratic. The Laplace transform is linear, So I apply it to each piece. 4t squared becomes 8 over s cubed. Negative 4t becomes negative 4 over s squared. 10 becomes 10 over s. Those are all from the patterns for powers of t in the tables. The 3 can then come over. The minus 3 will become plus 3. On the right, I can factor s squared plus 4s out of the y terms on the left, divide by that. If I take all of that to common denominator on the right, I get this expression. Again, this is going to need partial fractions. I have something over s cubed, something over s squared plus 4. The partial fractions done by computer gives me this. This still needs some work. This isn't exactly in the form I need, but I can split up the numerators and get 5 terms out of all of this. So the process here is to isolate capital Y however I can. Common denominator, that's set up. Use partial fractions to split it up, and then split up the numerators to get terms that I can actually understand. These 5 terms I can just look up on the tables and use inverse transforms, and I get the quadratics in sine and cosine as you see here. One of the amazing things about Laplace transforms is that they deal with discontinuous functions. So say I have a forcing term that only starts after a particular while. So my forcing term is 3 cos t, but it doesn't start right away. So I want to use this forcing term in the Laplace transform with a system that starts at rest, so 0 initial conditions. So this thing's at rest, but at time equals pi, some forcing term is going to come into effect. What's going to happen to that? Well, I transform the left, which is pretty easy. Y double prime becomes s squared y. The other 2 terms that I normally get there are 0 from the initial conditions. Lowercase y becomes uppercase y. And then I need to transform this weird discontinuous thing. I could do the integrals directly, but this is just a shift. This is just a step function multiplied by the cosine. It says the cosine starts at pi and before that 0. Well, that's the same as multiplying by the step function u pi. I can pull the 3 out for linearity, and I get this Laplace transform. This is pretty close to something that's on the tables, but it doesn't quite match up, because on the tables, if I have a step function ua, then the variable has to be t minus a inside the function. Here I can do some tricks with trigonometry. If I multiply by -1, the cosine of t and the cosine of t minus pi are offset by half a period. It's going to give me exactly the negative. So I can think of this as negative step function u pi times cosine of t minus pi. The point here is I'm manipulating it using all the tools I have, in this case understanding shifts in trig functions, to make this look like something from the tables that I can then apply transforms. This shift becomes an exponential in the t domain, multiplied by the transform of the cosine, which is s over s squared plus 1. So a little bit of work, but this forcing term does transform into this expression in the s domain. All right, then I have this setup. I isolate y on the left, divide by s squared plus 1, and I get this setup. I'd like to invert this to find the solution, but I have s squared plus 1 squared now when I divide by the second s squared plus 1. This is a bit tricky. But again, when I have powers like this in the denominator, I can think of these as derivatives of the single power of 1 over s squared plus 1. So if I set up the derivative, get the signs right, a 1/2 comes out, I get that this s over s squared plus 1 squared is the derivative of -1 over s squared plus 1 up to a 1/2. And this 1/2 can come out to get -3 out in front. This e to the negative pi s is going to turn into a step function. And this derivative is going to turn into multiplication by the variable. But the variable has been shifted. So it's not multiplication by t, it's multiplication by t minus pi. So this derivative here would transform into sine t, into t sine t. But this shift applies is going to be t minus pi sine t minus pi. So the exponential and the derivative give me this shifted expression at the end. And this is my solution. This is what's going to happen under this discontinuous force. Nothing's going to happen until time equals pi, and then this is going to start giving me a sine wave with linearly increasing amplitude. One last example. This one I want to do quite generally, just to show you that the machinery works even if I'm speaking in general. I want to look at harmonic motion in the case where there is oscillation, the underdamped case. So b squared minus 4mk in harmonic motion less than 0. And I want to look at it with no initial conditions, so at rest. And I want to see what happens to this system. At rest, the system will do nothing. So we should expect to get a zero solution here. But what if I actually change the initial conditions and have 1 and negative b over 2m? That's a bit of a strange setup, but work with it here to see what happens. I want to see if I can work this out in general with m, b, and k arbitrary to get a full description of harmonic motion. So I apply the Laplace transform, 0 goes to 0, the left side goes to these three terms, I fill in the initial conditions, and what I get out of that is this equation. I isolate capital Y, pulling it over, dividing by ms squared plus bs plus k, and I get this expression. I divide through by m to get this. Now what I want to do here, and this is instructive, is I want to complete the square in the denominator. Often completing the square is going to be necessary to match the pattern. So if I take these first two terms, s squared plus b over ms, and complete the square, the completion will be b squared over 4m squared. And then I have to subtract that same term after to balance it out. So completing the square gives me this, and I can see explicitly there it says s plus b over 2m squared. And in common denominator, this is the term that I get in the other part. All right, that's the expression I had. Let me label alpha and beta. These are actually the same alpha and beta that we did in Unit 3 on harmonic motion. So alpha is b over 2m, beta is the square root over 2m. Then this expression and this expression squared, this is alpha and alpha squared. And this expression is beta squared. So what I have is here is s plus alpha in the numerator, s plus alpha squared plus beta squared in the denominator. And this is in the tables. The trick with all of these is to say, all right, in the S domain, I get these expressions. How can I manipulate these expressions to look like something in the tables? Here it was completing the square. This transforms back to e to the alpha t cos beta t. So this whole thing, using alpha and beta in the way I just did, transforms back to this expression. And this is exactly what I wanted. I wanted harmonic motion with some initial conditions, and I get decayed oscillations of a cosine function. So this does work in general, assuming that m, k, and b are positive, and assuming that this is an underdamped situation, which means that this square root all the way through actually makes sense. And that's the theory. There's some more detail in some of the examples in the notes, and we can talk about that in class, but that's the basic idea. Laplace transforms takes a differential equation, makes an algebraic equation, which we have to work with using all the tools we have, completing squares, trig identities, various other types of tools to make it reasonable to undo the transform. But the solving now just becomes algebraic solving. And that's the real power, algebraic solving to solve differential equations.